particular solution of a differential equation. To start, let's look back at what we covered in our previous subsection, where we discussed the general solution of a differential equation. As you'll remember, a general solution doesn't just give us one single answer. Instead, it represents an entire family of curves. This is because the solution contains what we call arbitrary constants. These are symbols like C, A, or B, which can take on any numerical value. However, it is important to realize that in many practical and scientific applications, whether you are studying physics, engineering, or biology, we are rarely looking for an entire family of functions. In the real world, we are usually searching for one specific function that fits a particular set of known conditions or observations. This brings us to our main topic for today, the concept of a particular solution, which allows us to narrow down that broad family of curves to the one single, specific solution we need. Welcome, everyone. Let's begin our lesson on the particular solution of a differential equation. Understanding the particular solution. Now that we have established that the general solution represents a whole family of possible curves, let's dive deeper into what it actually means to find a particular solution. First, let's define it. A particular solution is a solution to a differential equation that is completely free from any arbitrary constants. You'll remember from our previous slide that the general solution always contains those placeholders, like C, or B. In a particular solution, those placeholders are gone. To put this in perspective, think of it this way. While the general solution provides the general form of the answer, essentially a template for all possible answers, the particular solution is the specific answer we are actually looking for. We obtain this specific version by assigning concrete numerical values to those arbitrary constants we found in the general solution. But how do we know which numbers to pick? We don't just guess. To find these specific values, we are usually provided with additional information known as initial conditions or boundary conditions. These conditions are essentially clues. They are specific points, which we represent as x and y, that the solution curve must pass through. In the next slide, I will show you the exact step-by-step process we use to apply these points to our equation to lock in that single, unique solution. How to derive a particular solution, step by step. Now that we understand the theoretical difference between a general and a particular solution, let's look at the practical side. You might be wondering, how do I actually perform this transition? Well, the process of moving from a general solution to a particular solution can be broken down into 4 very manageable steps. Step 1. First, you must identify the general solution. Before you can find a specific answer, you need to start with the general solution of your differential equation. As we mentioned in the previous slides, this is the version of the equation that still contains one or more arbitrary constants, such as y equals f of x, c. Step 2. Next, you apply the given conditions. This is where we use that extra information I mentioned earlier, the initial or boundary conditions. You will take the specific values provided for your independent variable, which is usually x, and your dependent variable, which is usually y, and substitute them directly into your general solution. Step 3. Once you have substituted those values, you must solve for the constant. At this stage, your equation will only have one unknown left. The arbitrary constant, like c, you will perform your algebraic calculations, adding, subtracting, or multiplying, to isolate that constant and find its specific numerical value. Finally, step 4, rewrite the final equation. Now that you have found the value of c, you aren't finished yet. You must substitute that specific numerical value back into your original general equation. Once you do this, you'll have an equation that is now devoid of any arbitrary constants. This final, specific equation is what we call your particular solution. In the next slide, we are going to see this exact 4-step process in action with some concrete mathematical and real-world examples. Illustrative examples. Now that we have understood the theory and the step-by-step process, let's put it into practice with two different types of examples. First, let's look at a straightforward mathematical derivation. Suppose we are presented with a general solution to a differential and equation, which is y equals x squared plus c. Our goal is to find the particular solution that specifically passes through the point, with an x-coordinate of 2 and a y-coordinate of 7. To solve this, we follow the steps we just discussed. First, we identify our general solution. Y equals x squared plus c. Next, we look at our given condition. Since the curve passes through the point 2, 7, this tells us that when x equals 2, y must equal 7. Now we substitute these values into our equation, which gives us 7 equals 2 squared plus c. Simplifying 2 squared, we get 7 equals 4 plus c. From here, we solve for c by subtracting 4 from both sides, leaving us with c equals 3. Finally, to reach our goal, we substitute this specific value back into the general equation. This gives us our final particular solution, y equals x squared plus 3. Notice how the arbitrary constant c has been replaced by a specific number. Moving from pure math to a real-world application, let's look at example 2, which involves population growth in biology. In many biological models, the growth of a bacterial culture is represented by the differential equation dp, dt equals kp, where p represents the population and t represents time. The general solution for this type of growth is p of t equals c e to the power of kt. Now, let's say we are given an initial condition. At time 0, the population is 500 bacteria. We need to find the particular solution for the constant c. Following our steps, we start with the general solution, p of t equals c e to the power of kt. We then apply our condition. At t equals 0, p equals 500. When we substitute these values into the equation, we get 500 equals c e to the power of k times 0. Since any number raised to the power of 0 is 1, the expression simplifies beautifully to 500 equals c times 1, which simply means c equals 500. To finish, we substitute 500 back into our general formula. Our particular solution for this specific bacterial colony is p of t equals 500 e to the power of kt. As we move to the next slide, keep these steps in mind, as I will highlight some common pitfalls that can occur during this process. Common mistakes to avoid. First, let's talk about the most common error: confusing the general solution with the particular solution. I often see students perform the integration correctly, find the general solution with the constant c, and then simply stop there. You must remember that if a problem provides you with a specific point or an initial condition, just like we saw in the examples on the previous slide, your job isn't finished until you have solved for that constant. If the question gives you extra information, it is explicitly asking you to move beyond the general form and find that specific, unique curve. Second, be very careful with incorrect substitution. When you are plugging your values into the equation, you must be precise. Ensure that the value of your independent variable, which is usually x or t, is substituted into the correct position, and that your dependent variable, such as y or p, is substituted for the other. It sounds simple, but swapping these two values is a very easy mistake to make, and it will lead you to an entirely incorrect value for your constant. Finally, a word of caution regarding ignoring the constant. This is a mistake that actually happens much earlier in the problem, during the integration process. Some students forget to write the constant of integration, c, immediately after integrating. If you omit c at that stage, you've essentially lost the ability to find a particular solution altogether, because there is no constant left to solve for. Always, and I mean always, include the constant of integration in your general solution as your very first step after integrating. Now, before we wrap up today's lesson with our final summary, I want to pause and discuss some common pitfalls. Even if you understand the concept of moving from a general solution to a particular one, there are a few mistakes that frequently trip students up during exams. Keep these 3 points in mind, and you will avoid the most common traps in this topic. Now, let's move to our final slide to review the key takeaways from today's session. Key takeaways. First, let's revisit the definition. Remember, a particular solution is not just any solution. It is one specific member chosen from the entire family of general solutions. The defining characteristic here is that it contains no arbitrary constants. The C, or A, or B we saw in our earlier slides has been replaced by a specific number. Second, regarding the requirements. You cannot find a particular solution out of thin air. As we saw in our step-by-step guide, you must have two ingredients. You need the general solution first, and you must be provided with at least one initial or boundary condition, such as a specific point on a graph. Third, let's consider the nature of these solutions. Think back to our discussion on the general solution representing a family of curves. It's like a collection of many possible paths. However, once we apply those conditions, the particular solution represents a single, unique curve in the xy plane. There is no ambiguity. There is only one path that satisfies both the equation and the given point. Finally, if you want to remember the logic of this entire process, just remember this simple flow. We start with the general solution, we apply the initial conditions, and we arrive at the particular solution. All right, we have reached the end of our lesson, so let's take a moment to recap the key takeaways to ensure everything we've discussed today is clear. I hope this summary helps solidify your understanding. If you have any questions about the examples we worked through, feel free to ask. Great job today.